بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أحب أرحب بكم بالمحاضرة الثامنة لنا بهذا الفصل، الفصل الدراسي الثاني، مادة ال Antineoplastic Agents. هذه راح تكون Lecture 8 Part 1. Alright. مثل ما قلنا Anti-Cancer Agents. Today we are going to talk about matrix metalloproteinase inhibitors. So, what are matrix metalloproteinases? They are zinc-dependent enzymes that play an important role in metastasis. These are destructive enzymes, okay? So they destroy their substrates, play a role in the breakdown, normal turnover, and remodeling of the extracellular matrix, okay? Normally, and when we say normally, we mean normal cells, these activities are controlled, okay? But in cancer, there is an overexpression or overactive enzymes. They also play a role in releasing the VEGF, the vascular endothelial growth factor. Okay, I think you learned that from the previous lecture. From where? From storage depots in the extracellular matrix. How? Because they destroy the extracellular matrix. They break down the extracellular matrix, so they release the VEGF. There are 4 types of the matrix metalloproteinases, or like they call them MMPs, the collagenases, gelatinases, stromylines, and membrane type. They just call it MT. All right. So we said these are, we said these are destructive enzymes. So what reaction catalyzed by the collagenases as example? Let's take the collagenases as example for the MMPs. Okay, so as you know, collagen is made up of protein, right? So the enzyme, as we said, it's a destructive enzyme, so it is going to cut the protein. It is going to hydrolyze the peptide bond between glycine, okay? Let me do this. This is glycine, and either leucine or isoleucine. Okay, you see that? So it cuts this bond between the glycine and leucine, or either isoleucine. Okay, so what will happen? It will give you 2 or more proteins. Instead of 1 protein, it's gonna give you fragments of protein, and that's how they destroy or break down the matrix, the extracellular matrix. Okay, so as I mentioned, proteins are substrates for these enzymes. Enzyme hydrolyzes the peptide bond between glycine and either isoleucine or leucine, as you saw them. Okay, so what are the binding interactions between the substrate and the enzyme? And that's important. The binding interactions are important because we try to mimic those binding interactions in the inhibitor, as you saw earlier in our lectures and as you will see in this lecture also. Okay, this is the substrate for the enzyme. Okay, and let's assume that this whole thing is the enzyme. Okay, so the binding interactions, the zinc ion, as we said, it's a zinc metalloproteinase enzyme. So the zinc ion interacts with the susceptible carbonyl oxygen. Okay, it's this carbonyl. All right. It activates the peptide bond for hydrolysis. Why? Because when zinc interact with oxygen, it's gonna pull the lone pair of electrons. As you know, oxygen has 2 lone pair of electrons, so it's gonna pull those lone pair of electrons away, and that's gonna make this, that's gonna increase the positivity, make this partially positive. It is partially positive, but that's gonna increase the positivity. Okay, that what we mean by activate. Okay, the NH of the susceptible peptide forms a hydrogen bond to alanine of the enzyme. We said, as you know, we said this is the enzyme. So the NH is going to form a bond here. Okay. The bridging water molecule, this water molecule, okay, present between zinc cofactor and glutamate residue. And that's why we call it bridging, because it connects two entities, the zinc and the glutamate. Okay, the bridging water act as a nucleophile for the hydrolysis. Why? Because as you know, oxygen has 2 lone pair of electrons. Okay, when the glutamate, the negatively charged glutamate, pull those protons down, that's going to increase the negativity of this. Lead to that oxygen will attack the positively charged carbon of the carbonyl, and that will open this bond. Okay, leads to the hydrolysis. Okay, as I said, the bridging water is activated by glutamate and zinc. Okay, all right. So what about the inhibitors? We learned about the enzymes. Now let us talk about the inhibitors of the enzymes. Potential agents for inhibiting angiogenesis and metastasis. As we said earlier, these enzymes break down the extracellular matrix. If you break down the extracellular matrix, you are going to make way, okay, for cells to metastasize. So if you stop these enzymes, you stop the breakdown of the extracellular matrix, and that's how you inhibit the angiogenesis and metastasis. Well, you inhibit the angiogenesis because you are going to decrease the release of VEGF from the depots in the extracellular matrix. The first generation inhibitors are based on the substrate structure, okay? That's why we said it's important to learn the binding interactions of the substrate. Susceptible peptide bond is replaced with a stable transition state isoster, as you learned from previous lectures. If we have a susceptible bond, susceptible, that means it could be hydrolyzed or break down by enzymes. So we change that. We change it to another bond that is more stable but have the same or similar properties, okay? The hydrophobic substituents are present to fit the enzyme subsite. So it's just like the hydrophobic substituents of the substrate, okay? The substituents mimicking the P1 prime or P2 prime, which is the right-hand side inhibitors, are better than substituent mimicking P1 or P2, the left side hand inhibitors. So what is the right side? What is the left side? Let us go back here, show you the right and the left sides. Okay, just a minute. Okay, here it is. We said you have one peptide that's going to be broken down into two, right? So this is the right hand and this is the left hand. So substrates that mimics the right hand peptide are more active or more effective than those that mimic the left side. All right? I think you got it now. Well, I hope so. All right. The functional groups are included to form hydrogen bonds with the enzyme backbone, just like the substrate. We said the NH of the substrate makes hydrogen bond with the enzyme. So there are some functional groups to replace that, okay? A group is included to form strong interaction with the zinc ion cofactor. It's a zinc metalloproteinase enzyme. So we need a group that interact with the zinc ion. Zinc ligands commonly used are thiols, carboxylates, or hydroxamic acids. Okay, these are the groups that are commonly used as zinc ligands. All right. As we said, the first generation example on those is the marimestat. This is the structure of the marimestat. As you can see, it resembles the substrate of the enzyme. It has hydroxamic acid as the, let me do this. It has a hydroxamic acid as the zinc ligand. It has a T-butyl group or a T-butyl group to protect this bond from hydrolysis, which is a peptide bond. It's an amide bond. Okay. It also has transition state isoster, as we mentioned earlier. Okay. This is an orally active synthetic compound, so it is not a natural product. It is a synthetic compound. It reached first phase 3 clinical trials for breast and prostate cancer. The hydroxamic acid act as the zinc ligand. The hydroxymethylene group, this one, acts as the transition state isoster. It is not susceptible to hydrolysis, just like the NH or the amide group, sorry, the amide bond. The isoster replaced the NH of the previously susceptible peptide bond, as we mentioned earlier. The hydroxyl group of the isoster is good not only for activity, but it is also good for aqueous solubility. It's a hydroxyl group. It can form hydrogen bonding with water. Okay. Also, the T-butyl group, this one, act as a steric shield to protect the N-terminal amide from hydrolysis. This bond here, this one. Okay. And if you remember in our first semester, when we talked about the cholinergics and the anticholinergics, we said that you can use group as a shield to protect from hydrolysis, right? Okay, if you remember over there, they used just a small methyl group because the enzyme couldn't fit big groups. Now the scientists were able to use T-butyl group, which is larger, bigger than a small methyl. All right. The T-butyl group also desolvates peptide bond. Okay. Desolvate. So you don't have to suffer from the desolvation penalty. Okay. So no desolvation penalty for binding. Okay. Okay. So what are the binding interactions between the marimestat and the enzyme? These are the binding interactions. You see the zinc and you see the sub site or the subgroups of the enzymes. As you can see here, this is the P1 prime, P2 prime, and the P3 prime. And as we said earlier, the inhibitors that mimic the right-hand side of the peptide is more active than those mimic the left-hand side. Okay. We said the hydroxamic acid is the zinc ligand. As you can see here, the NH group here form a hydrogen bond with the enzyme. 3 hydrophobic substituent fit the enzyme subpockets. The subpocket 1 prime, 2 prime, and 3 primes. The substituents bind using van der Waals interactions because these are hydrophobic. Okay, so there is no hydrogen bond. So how they would interact? They will interact by van der Waals interactions. The hydroxamic acid act as a bidentate ligand for zinc. Bidentate, that means it has 2 sites for interactions, this one and that one. The hydroxamic acid NH act as a hydrogen bond donor. The alcohol group here, this one, is good for activity, as we said earlier, and it's also good for solubility. The alcohol group is directed away from the protein surface and forms a hydrogen bond with water, as we mentioned. All right. Okay, how about another example, the BMS 275291. This is the structure for the BMS 275291. You see here we have a thiol group as the zinc ligand and a hydantoin ring. But the right-hand side part is the same as the marimestat. It is the same, similar. The thiol group act as a zinc ligand. Sorry. Substituents P1 through P3 prime fit enzyme subpockets. The right hand half is identical to marimestat. Okay, so those are the first generation inhibitors. So how about the second generation? Well, first, why we need to design second generation inhibitors? There should be some aims, right? The aims to design the second generation inhibitors are to reduce or eliminate peptide character. Why? Because peptides have bad pharmacokinetic properties. Increase selectivity, because the first generation are not selective, they have a lot of side effects. So eventually decrease side effects and increase aqueous solubility. Okay. Also increase resistant to peptidases in gastrointestinal tract. Well, that's one of the reasons to reduce or eliminate the peptide character. All right. What are those second generation inhibitors? Example on those is the CGS 2723A. It has that steric shield. As you can see, it has less peptide character than the first generation. The hydroxamic acid act as a zinc ligand, so they kept the hydroxamic acid here. 2 substituents, the P1 prime, the P2 prime, those fit into the enzyme subpocket. As I mentioned, decreased peptide character, and the isopropyl group act as a steric shield, okay, to prevent the hydrolysis of these bonds. Thought to protect hydroxamic acid from metabolism. That's the reason why we are using the the steric shield. But unfortunately, it lacks selectivity. So this one lacks selectivity. All right. Another agent, which is also a second generation inhibitor, is the prenomastat. The prenomastat combines that steric shield and it combines the steric shield in a ring here. Okay, that is what design strategy. It's rigidification. Okay, and it has that pyridine, as I said, the rigidification strategy. The isopropyl substituent is incorporated into a ring. That is rigidification strategy. Less conformations are available, so decrease the conformation is better in this case, results in increased activity. The pyridine ring allows extra binding interaction, this pyridine ring, and that's called extension strategy. You see here it's just a methyl, but here it's a pyridine. So they extend the group. All right. Another example is the BAY 129655. It has a carboxylate as the zinc ligand. The carboxylate group acts as the zinc ligand for the zinc ion instead of using the hydroxamic acid or the thiol. The BAY 129655 reached clinical trials. Now, what are the future aims for the matrix metalloproteinase inhibitors? None of the matrix metalloproteinases studied so far have reached the clinic. So as you saw, marimastat, prenomastat, the BAY inhibitor, all of them in clinical trials. Why? Because greater selectivity is required. And agents with selectivity for MMP or matrix metalloproteinase 2, 9, and 14 are of interest. Also for 25. Okay. Why these are of interest? Because they are crucial to angiogenesis and metastasis. The depth and flexibility of the S1' pocket varies between different MMPs, which means it is possible approach is to design agents where the interactions with the S1' pocket are crucial for activity rather than agents with strong zinc binding ligands. Why? Because they tried the agents with strong zinc binding ligand, but they couldn't get activity. So they are going to try different approaches. And thank you for listening. We are going to continue with the second part of this